Eleanor Whitmore was 20 years old when her Aunt Constance made it clear she was no longer welcome in the family home. It was June 1891 in Burlington, Vermont, and Constance Hood inherited the house from Eleanor's uncle after his death 3 months earlier, had her own plans that didn't include supporting her late husband's niece indefinitely. Eleanor's parents had died in a typhoid outbreak when she was 16. Her uncle Richard Whitmore, a wealthy merchant with no children of his own, had taken her in and paid for her education, including unusual subjects like mathematics and natural philosophy that most people considered inappropriate for women. Richard had been a patron of science and believed Eleanor had an exceptional mind worth cultivating. But Richard died in March 1891, leaving everything to his wife Constance rather than establishing any provision for Eleanor. Constance, who'd always resented Richard's attention to his niece, gave Eleanor 3 months to find her own situation, offered her $100, generous in absolute terms but clearly intended as final settlement with no ongoing support. Eleanor took the $100 and made a choice that combined her education, her circumstances, and a property nobody else wanted, an abandoned stone observatory on a hilltop 3 miles outside Burlington. The observatory had been built in 1878 by a wealthy amateur astronomer named Dr. James Crawford. He'd constructed it at considerable expense's circular stone tower, 20 feet in diameter, 25 feet high, with walls 3 feet thick, built from local limestone blocks. The structure had housed a refracting telescope in a rotating wooden dome that could be opened to observe the night sky. Dr. Crawford had died in 8. His heirs had no interest in astronomy. They'd removed the valuable telescope and sold it. The wooden dome had deteriorated from 6 years of weather exposure. The building was considered worthless, a peculiar stone tower in an isolated location with no practical use. The property was in tax default. Nobody wanted it. Eleanor saw something different. She saw a circular stone structure with 3-foot thick walls, massive thermal mass that would moderate temperature swings. She saw a building that was fundamentally weathertight despite the damaged dome. She saw a location with southern exposure and elevation that would maximize winter sun. And she saw something she could potentially afford. She approached the tax collector's office in Burlington. The observatory property, 1 acre of hilltop land with the stone tower, had accumulated $62 in back taxes over 6 years. If Eleanor paid the taxes, the property would be hers through tax sale. $62 of her $100 stake would secure ownership of a unique structure. She paid the taxes in early July, legally purchased the abandoned observatory, had $38 remaining to make it habitable before Vermont winter arrived. The structure's condition was simultaneously encouraging and daunting. The stone walls were intact, solid limestone masonry, showing no cracks or settlement. The circular design was structurally stable, but the wooden dome had rotted badly. The interior was bare stone, no floor beyond packed earth, no furnishings, no amenities. The single door was present, but warped. There were narrow observation slits around the upper walls, but no conventional windows. Her plan combined her education in natural philosophy with practical necessity. She'd convert the observatory into living space by addressing critical needs: weatherproof roof, proper floor, heating system, windows for light. But she'd do it intelligently, using the building's inherent advantages rather than fighting against its unusual design. The circular shape provided structural and thermal advantages she understood from her studies. A circle has minimum surface area for given volume, meaning less wall area, losing heat, compared to a rectangular building of similar size. The 3-foot-thick stone walls provided enormous thermal mass, perhaps 60 tons of limestone, that would absorb heat slowly and release it slowly, moderating temperature extremes. For the roof, she couldn't afford to rebuild a rotating dome that would require skilled carpentry and expensive materials she didn't have. Instead, she'd build a simple conical roof that would be cheaper, simpler to construct working alone, and actually more weathertight than the complex dome design. She bought rough-cut lumber with $20 8 12-foot rafters for the main structural members, additional boards for sheathing, and corrugated tin sheets for waterproof covering, carried it all up the hill in multiple trips, loading lumber onto a borrowed handcart and pushing it the 3 miles from Burlington. The construction required solving unique problems. The stone tower had no conventional roof plate to attach rafters. Instead, she built a wooden ring beam that sat atop the circular walls, essentially a circular plate that would receive the rafters. She positioned this beam carefully, checking level in multiple directions, securing it to the stone with iron spikes driven into mortar joints. The rafters were challenging. In a conventional peaked roof, rafters meet at a central ridge beam. In a conical design radiating from a point, all 8 rafters needed to meet at apex with precise angles. She calculated the geometry carefully. The tower was 20 feet in diameter, requiring each rafter to span from the 10-foot radius to center. At 25-foot wall height plus desired roof pitch, she needed rafters cut at specific compound angles. She worked methodically through late July, fitting each rafter individually, cut the bottom angle to match the circular ring beam curvature, cut the top angle so all 8 would meet cleanly at apex, lifted each heavy timber into position. Difficult solo work, requiring temporary bracing to hold rafters while she secured them. The physical challenge was extraordinary's heed lever, a rafter up using a makeshift pulley system, balance it on temporary supports, climb up to secure it, repeat 8 times. By early August, the rafter framework stood 8 timbers, radiating from central peak like spokes of a wheel. She covered them with horizontal boards, running from ring beam to apex, creating solid sheathing. Then came the tin she cut corrugated sheets to fit the cone, nailing them with overlapping seams to shed water. The work took 2 full weeks, working dawn to dusk. The finished roof looked crude, gray tin cone, sitting atop elegant limestone tower, but it was functional, weathertight, and had cost just $20 in materials versus the hundreds a dome reconstruction would have required. For the floor, she needed insulation from the earth, bought load of sawdust for $3, and spread it 6 inches thick across the entire circular floor. Over the sawdust, she laid salvaged boards she gathered from abandoned buildings, created a raised wooden floor that was insulated from ground cold. For windows, she couldn't afford glass for large openings, but the existing observation slits narrow openings designed for telescope view and could be fitted with salvaged glass to provide light while minimizing heat loss. She found old window panes at a salvage yard for $2, cut and fitted them into the slits. The result was unusual but functional narrow windows around the circumference, providing natural light without large heat-losing openings. For heating, she built a small stone firebox in the center of the circular space, used stones from the property to construct a combustion chamber, maybe 2 feet square. The central location was deliberate. Heat from a central source would radiate evenly to all parts of the circular room. In a rectangular room, a corner stove creates hot and cold zones. In a circular room with central heating, temperature would be nearly uniform throughout. She installed a metal stovepipe, rising straight up through the center of the conical roof. Simple but effective, no complex chimney required, just vertical pipe from central firebox exiting through roof peak. By September, the structure was habitable. The rough conversion had consumed 98 of her $100. She had $2 remaining, but she owned a unique dwelling that cost nothing to rent and would cost minimal fuel to heat through winter. The interior was undeniably unusual. A circular room, 20 feet in diameter, 314 square feet of floor space. Stone walls curving around the perimeter. Narrow windows providing strips of light. Rough wooden floor. Central stone firebox. Crude but functional furniture she built from salvaged lumber, a bed frame, a table, 2 chairs, shelves mounted to the stone walls. She found work in Burlington at a textile mill, $12 weekly, extraordinary wages for women's work in 1891, but justified by her mathematical ability that made her valuable for quality control calculations. Would walk the 3 miles each way daily. Lived frugally in her stone tower, saving most of her income. The town's reaction when people discovered where she was living ranged from shock to fascination. Living in an abandoned observatory, alone, at 20 years old, the respectable women of Burlington considered it scandalous. The practical men considered it peculiar but economical. Everyone expected she'd suffer terribly when winter came. Margaret Blackwell, wife of a prominent lawyer and pillar of Burlington society, organized a visit in October. 5 women came to convince Eleanor to accept proper boarding arrangements. They arrived at the hilltop and stopped, staring at the stone tower with its crude, conical tin roof. It looked like a medieval fortress that had been capped with a farmer's grain silo. They entered through the warped door and stopped again, trying to process the circular interior. The stone walls curving around, the narrow slit windows, the central stone firebox, the rough furniture, the whole space felt like someone had tried to make a home inside a castle turret. "Miss Whitmore," Margaret said carefully, "you're living in a stone tower on a hill. This is not appropriate housing for a young woman. It's isolated, it's primitive. When winter comes, stone walls will be freezing cold. You need proper lodging before you freeze, or worse. The stone walls provide thermal mass. The circular design minimizes heat loss. The central heating location provides even temperature distribution. The structure is actually well suited to efficient winter habitation. It's a stone tower designed for telescopes, not people. Stone is cold. Everyone knows that. Please accept the Morrison family's offer. They need household help. Room and board, plus $4 weekly. That's proper housing." Eleanor thanked them for their concern and watched them leave, certain she'd be dead or broken by January. Through October and November, the observatory proved remarkably effective as housing, and Eleanor began understanding thermal advantages she hadn't fully anticipated, advantages that her education in natural philosophy helped her recognize and quantify. The massive stone walls, 3 feet thick, 60 tons of limestone, acted as enormous thermal battery in ways that exceeded her initial calculations. She'd understood theoretically that thermal mass would moderate temperature, but experiencing it daily revealed nuances theory couldn't capture. During sunny October days, even with temperatures in the 40s or 50s, outside, the south-facing portions of the stone walls would absorb solar radiation. The stone warmed slowly, perhaps 1 degree per hour of sun exposure. By afternoon, the sun-facing wall sections would be noticeably warmer than morning temperature. That warmth would gradually conduct through the 3-foot thickness, reaching the interior surfaces by evening. After sunset, the stored heat would radiate inward. The room temperature would rise slightly in evening despite outside temperature dropping, a counterintuitive effect where interior got warmer as exterior got colder. The thermal mass was releasing stored daytime heat through the night. She began documenting this with thermometer readings. On a typical October day, outside temperature ranged from 40 degrees at dawn to 55 at afternoon to 45 at evening. Interior temperature with no fire ranged from 52 degrees at dawn to 54 at afternoon to 55 at evening. The stone walls were damping the temperature swings and creating a thermal lag interior. Temperature peaked hours after exterior temperature. The circular shape provided unexpected benefits beyond simple geometry. She'd calculated that a circle minimized surface area for given volume. Basic mathematics she'd learned, but she hadn't fully appreciated how wind interaction would change with curved versus flat surfaces. During November windstorms, sustained 30 to 40 mile-per-hour winds, common in Vermont autumn, she observed the difference dramatically. Wind hitting her circular tower would flow smoothly around the curved stone. No flat surfaces for wind to push against. No corners where pressure could concentrate and find gaps in construction. The wind would roar outside. She could hear it clearly, but inside felt remarkably still. Minimal drafts, minimal pressure changes. The aerodynamics of the circle protecting the interior. The central heating location was brilliantly efficient. She'd build a small fire in the stone firebox, maybe 4 or 5 pieces of wood. The heat would radiate outward equally in all directions. Because the heating source was centered in the circular space, every part of the room was equidistant from heat. No cold corners, no hot spots, just even warmth spreading outward from center. Her fuel consumption was extraordinarily low. The 3-foot stone walls provided perhaps our 6 insulation value, exceptional but adequate. The circular design minimized surface area. The central heating location maximized efficiency. She burned approximately half a cord of wood per month through November, significantly less than the cord or more that conventional houses required. December brought cold that tested everything. Temperature dropped to 0 degrees at night. Eleanor's observatory maintained stable conditions. The stone walls, once warmed by her small evening fires, would hold that heat for hours. She'd burn a fire from 6 to 10 p.m. By 10 p.m., the interior would be 65 degrees. The stone walls would be perhaps 60 degrees throughout their 3-foot thickness. After the fire died, the room would cool slowly. By midnight, 58 degrees. By 6 a.m., 50 degrees. The stone walls were releasing stored heat all night. She'd wake in a 50-degree room cool, but not freezing, and build her morning fire. The cycle repeated daily with minimal fuel consumption. Her Aunt Constance's house, conventional wood frame construction with thin walls, couldn't maintain 55 degrees despite burning wood continuously. The thin walls lost heat rapidly. Conventional corner or wall-mounted stoves created uneven heating. They burned perhaps 5 cords monthly, maintaining barely adequate temperature. Then January brought the cold snap that proved everything and transformed how Burlington understood the relationship between building design and winter survival. The cold arrived January 8th with warning signs that veteran Vermont residents recognized immediately as dangerous. Mornings started at 10 degrees cold, but normal for January. By noon, 0 degrees. By 6 p.m., -10, by midnight, -15, by dawn, January 9th, -20 degrees. The temperature wasn't just cold, it was sustained cold. -20 through January 9th. -20 to January 10th. Back to -20, January 11th. The Arctic air mass had settled over Vermont and wasn't moving. No warming trend, no moderation, just relentless, extreme cold that would last 9 days total and expose every flaw in every building's thermal design. The wind made survival conditions even harsher. Sustained 15 miles per hour with gusts to 30. Wind chill pushed effective temperature to -40 or colder. Exposed skin froze in under 3 minutes. Breathing unfiltered outdoor air caused immediate lung pain and coughing. Walking any distance became genuinely dangerous. Eleanor's stone observatory maintained remarkable stability through the entire cold snap, and her thermometer readings documented performance that contradicted conventional assumptions about stone buildings. The massive walls, 60 tons of limestone at roughly 55 degrees average temperature when the cold snap began, contained enormous stored thermal energy. She calculated roughly 60 tons equals 120,000 pounds. Limestone has specific heat of roughly 0.2 BTU per pound per degree Fahrenheit. If the walls were at 55 degrees and cooled to 50 degrees, that 5-degree drop would release 120,000 pounds times 5 degrees times 0. To BTU, that was 120,000 BTU of stored energy released just from the walls, cooling 5 degrees. That stored energy meant the cold outside couldn't penetrate rapidly. She'd burn her normal evening fires, small amounts of wood, from 6 to 10 p.m., perhaps 6 pieces total. The fire would warm the interior air to 65 degrees. More importantly, it would warm the interior surface of the stone walls. Heat would conduct slowly inward through the 3-foot thickness, warming the massive thermal mass. After the fire died at 10 p.m., the room would cool slowly. By midnight, 60 degrees. By 3 a.m., 55 degrees. By 6 a.m., 50 degrees. The stone walls were releasing stored heat continuously. Without those walls, a thin-walled building would match outdoor temperature within 3 to 4 hours of the fire dying. With 60 tons of thermal mass, temperature changes occurred over 12 to 16 hours. Her fuel consumption during the cold snap was essentially unchanged from normal December conditions, maybe half a quart for the 9-day period. She burned the same small evening fires she'd always burned. The thermal mass did the rest. Conventional houses in Burlington were failing catastrophically by day 3. The Blackwell house, well built by 1890 standards with plaster walls and proper heating, could maintain 50 degrees. Despite burning wood continuously day and night in both the parlor stove and the kitchen stove, they'd feed wood every hour, keeping fires going around the clock. Watching interior temperature hover between 48 and 52 degrees, depending on wind and how recently they'd added fuel. Their wood consumption was unsustainable. They burned approximately 1.5 cords in the first 4 days, wood that should have lasted 6 weeks at normal rates. At current consumption, they'd deplete their winter supply within 3 weeks, with 2 months of winter remaining. The mathematics were impossible. They'd have to buy emergency wood at winter prices or start burning furniture. The Morrison family situation was worse. Their house had been cheaply built with minimal insulation. Cold air infiltrated through gaps around windows and doors. Heat escaped through thin walls and inadequately insulated attic. By day, for January 11th, their house was 43 degrees. Inside, despite burning wood desperately and burning some furniture when wood ran low, their children were wearing every piece of clothing they owned, layered together, and still showing signs of cold exposure. On day 6, Margaret Blackwell's husband came to the observatory, something he'd considered beneath his dignity previously, but desperation overrode pride. Found Eleanor comfortable in her circular stone room. "How is this warm?" he asked bluntly. "My house, with proper heating, can't stay above 50 degrees. Your stone tower is clearly warmer." "How?" Eleanor showed him the system. The massive stone walls providing thermal mass, the central heating location distributing heat evenly, the circular design minimizing heat loss, the whole structure functioning as a thermal battery that charged during fires and discharged heat slowly for hours afterward. Stone stores heat. Your thin wooden walls don't. When I burn a fire, the heat soaks into 3 feet of limestone. 60 tons of stone, warming by 10 degrees, stores enormous energy. After the fire dies, that stored heat radiates inward for 8 to 12 hours. I'm not trying to maintain temperature with continuous burning. I'm charging a thermal battery with short burns and living off the stored energy. But stone is cold. Everyone knows stone buildings are cold. Thin stone walls without heating are cold. Thick stone walls with regular heating are thermal batteries. The thickness is everything. Your thin walls provide no thermal mass. My 3-foot walls are massive heat storage. By day 8, 20 families had visited the observatory, and what they found challenged every assumption they held about stone buildings, heating systems, and appropriate architecture for Vermont winters. The visits followed a pattern. Families would climb the hilltop in -20 cold, frost-covered, and skeptical. They'd been told the Whitmore woman was somehow comfortable in her stone tower, but nobody believed stone could be warm. Stone was cold, everyone knew that. Churches were cold. Stone cellars were cold. Stone buildings were inherently frigid. They'd knock on the warped door. Eleanor would open it. Warm air would roll out, not blazing hot, but noticeably warm. Maybe 55 to 60 degrees, depending on time relative to her last fire. After walking through -20 wind, 55 felt like genuine warmth. They'd enter the circular interior and stop completely. The stone walls that should be ice cold to touch were actually neutral temperature, maybe 55 degrees at the interior surface. Not hot, but not the bone-chilling cold they expected. The narrow windows with their improvised glass somehow weren't leaking cold. The space felt warmer than their conventional houses, despite Eleanor burning far less wood. "How?" they'd ask, touching the stone walls with disbelief. "Stone is cold. How is this warm?" Eleanor would explain patiently, repeatedly, to group after group. The massive walls stored heat. The 3-foot thickness meant slow heat transfer. The circular design minimized surface area. The central heating location distributed warmth evenly. Everything about the structure's geometry and mass worked together to create thermal stability. She'd show them her thermometer readings, document the slow temperature changes, explain the physics of thermal mass and heat capacity. Some understood immediately, particularly men with engineering or scientific background. Others remained skeptical, attributing her comfort to luck or some factor they couldn't identify. But the mathematics were undeniable. She was burning half a cord every 9 days during the worst cold snap Vermont had seen in years. They were burning 1 to 2 cords per 9 days and still couldn't maintain adequate temperature. The efficiency difference was too dramatic to dismiss. By day January 15th, the community understanding began shifting. Margaret Blackwell came personally, having sent her husband days earlier, stood in the circular room, feeling genuine warmth, despite -20 outside. Understood that she'd been completely wrong about the stone tower being inappropriate housing. "Miss Whitmore, I owe you an apology," she said quietly. "When you moved here, I thought you were making terrible mistake. Thought you'd suffer terribly or die. Instead, you've created shelter that outperforms every proper house in Burlington. My house, with expensive heating, can barely stay above freezing. Your stone tower is comfortable. I was wrong." Eleanor could have been vindictive, could have pointed out the months of mockery and pressure to accept proper arrangements. Instead, she was generous and educational. "You weren't wrong to be concerned. Unconventional housing is risky, but you were wrong about stone being inherently cold. Thin stone is cold. Massive stone is thermal battery. The thickness is everything. Your thin walls, whether wood or plaster, provide no thermal mass. They're just barriers that slow heat loss. My walls are heat storage that releases energy for hours after fires die." Could this design be replicated? Could conventional houses incorporate these principles, partially? Building new circular stone houses would be expensive, but existing houses could add thermal mass stone or masonry interior walls that absorb and release heat. Central heating is more efficient than corner stoves. Understanding thermal lag, how mass delays temperature changes, allows better heating strategies. The transformation wasn't just individual understanding, it rippled through Burlington's building practices. By spring 1892, 2 families had hired masons to build interior stone walls in their houses, specifically for thermal mass. 3 families had moved heating stoves from corners to more central locations. The concept that thermal mass matters was spreading. Eleanor became an unexpected consultant. At 21 years old, she was advising experienced builders on thermal efficiency, heat storage, and the physics of comfortable housing. Some builders resented taking advice from a woman barely past 20. Others recognized that her education and practical experience gave her knowledge they lacked. She began publishing articles in scientific journals about residential thermal efficiency. Her observatory conversion became a case study, documented temperature readings showing how massive walls damped temperature swings and reduced fuel consumption. The papers attracted attention from engineering societies and progressive architects interested in efficient design. She lived in the observatory for 8 years, published papers on thermal efficiency and residential design that attracted attention from engineering societies. Married at 28, a professor of natural philosophy who appreciated her scientific work and understood the value of her observatory conversion. They eventually built a larger house, but kept the observatory as a study and demonstration of thermal mass principles. Eleanor became a consulting engineer, specializing in efficient building design, revolutionary for a woman in the 1890s. She died in 1942 at age 71. Her obituary mentioned her engineering work, but focused primarily on the observatory. The abandoned stone tower converted into efficient housing using principles of thermal mass, geometry, and central heating that proved superior to conventional construction. The observatory still stands, owned by the University of Vermont's Physics Department. Modern thermal analysis confirms the efficiency. The 3-foot limestone walls provide massive heat storage capacity. During the cold snap, the structure maintained livable conditions with 1/10 the fuel consumption of conventional buildings. The story is about a young woman who understood that luxury isn't about expensive finishes, it's about comfort achieved through understanding physics, who proved that unconventional buildings can outperform conventional ones when you understand thermal mass and geometry, and whose castle outperformed everyone's regular houses because science matters more than tradition.